Yeah, everyone. Good afternoon once again. I think most of the people keep on joining, so we have to be careful. We let them in into the meeting. Right. So welcome on board, everyone. So today's seminar is about the design flow, basic design flow, what you have to follow or what you can follow, and we'll have structural design knowledge also. So. There are team from John Deere who are joining us today, but there are few things which I would like to make clear. Whatever content we have used in this presentation, they are made by themselves. Like we are not allowed to use any other content from any other website or book. You might be having a very good content already, so make sure on every topic, if you have any question, we have experts with us. You can directly ask them because there will be so many data which is already there, which we are not able to place in the presentation. So make sure to stay active on the topics and keep on asking the question. So the content will be something like this, which you are seeing on the screen right now. Uh, the first deviation, it is very important, so be very attentive. It is deviation from the rule book which we are providing to the team. I'll cover that in the coming slide. Then how your design flow should be, how you can start or initiate your design work like through basic calculation or basic sketching. Then we'll have slides on material selection, then hardware, bearing, welding, jig and fixture. All the basics we are trying to cover over here so that it can give you a good kickoff. Okay, so talking about this deviation, so in the rule book, am I audible, Ajay?
Yeah, please
Okay,
continue.
yeah.
Yes.
So in the rule book, there is one point in the pickup system where we are providing the dimension of sapling tray, which will be giving. So there are so many challenges which we heard from the teams and the student that it would be difficult to pick up the sapling from this dense sapling tray which we are providing. So we'll be giving one liberty to the students that they can have their own sapling tray designed or customized, but make sure there are few points which needs to be taken care. The tray should have minimum of 90 saplings holding capacity. Like it is a minimum, maximum it's on your wish, and you should be having at least four customized tray of minimum 90 sapling holding capacity. Uh, the cup dimension which
So it's a kind request, Krishna, Venu, can you mute?
guys who are not speaking, can you mute the mic? Okay, thank you.
So I'll do one thing. I'll mute everybody and
Mhm.
make you as a co-host, sir. You can unmute and mute yourself.
Yeah, thank you, Aisha.
Thanks.
Okay, so the reason of providing this liberty is like whenever we are working on any of the production system, it should be start from zero. So the tree which we are providing, definitely they might not be compatible with the implements what you are designing, and we don't want to force you to use the existing system. If you can design your implement in such a way that your own customized tree will work best with your implement, then you are free to do that. Definitely, the saplings will be provided by us only, and you have to transfer those saplings in your customized tray. Make sure that tree is removable, like the normal tray. You can simply place it and remove it from your implement. Then placing of this tray into the implement, it is not counted as manual intervention. Then while transferring the sapling, make sure any of the OC member is present in front of you so that you won't damage any of the saplings which we have provided. because that bulb with the sapling, it comes out very easily and it is very easy to transfer the sapling into your customized tray. Once you transfer the sapling, you can place that into the implement. So that is the deviation which we are providing. If you have any other question, you can ask your mentors, and we'll be circulating this document most probably early next week. So all the captains will get it in the mail. Okay, then I think we might have already shared this verbally, but this is something which you should be following as a team. So you are already done with the registration and team formation. You might have understand the rule book. Make sure that you have assigned the roles and responsibilities properly within the team, like which student will be responsible for what role. Then you might have to do this market study also, like what all implements are already there, whether they are mechanical, semi-automatic or automatic, and understand about the some vegetable agronomy also. And we did that session already. Then try to work on the subsystem individually or as a group of small students, like do brainstorm, idea sketching, calculation, whatever requirement we have mentioned in the rule book, make sure to follow those constraints and start working. Then in parallel, as soon as you got the ideas, you have done the CAD modeling, designing, start putting into the design template. And make sure to go through this template first so that you'll come to know what all things you need to calculate, model, or design to put it in the template. Then definitely you can do the complete CAD model virtually, and you can do all the analysis or simulation of your mechanisms virtually. Then this is just an example that in such a way you should be preparing your team format, like who are your CAD lead, design lead, marketing lead, or costing, manufacturing lead, something kind, like it's completely on your team formation, what are leads you want, and how many students will be there under that lead. Definitely, the team is not that big, but still, if there is one point of contact for any specific area, it will be easy for you to go ahead. Then do prepare this type of project plan. It's just an example template we have prepared. So you can note down all the parameters over here which is required for the phase one. Then you can add for the phase two as well. I've just given few of the example of phase one, like when you should be starting. Like you have started from the registration, say 2nd of October. Then what all things you want to pursue further with some major milestone that yeah is by the end of the October we should be at least ready with all the market study roles and responsibility, everything done till here in October. Then we can start working on the CAD modeling or design part, say from November. And what all things you can do in parallel, you can divide it in the team. So this will help you keep a track what all things you have done and what all things you have to do going forward. Okay, so this is the basic operation which we have given you that your implement should be capable of performing. So we tried just rough sketching, like how you can start. I am showing on the implement level. You can do it on the subsystem level as well. Like say, we have given you a box dimension of 2000 by 2500 by 1800 mm. So what you can do, you can just keep this as your constraint. Then you can try placing the sapling tray, like it could be on the top of the implement or somewhere in the middle of the implement. That's completely on you. Then what are the major subsystem which you have to accommodate in this box? You can simply place it by sketching it down. So every team must be having small group formed which will be doing the specific task on of subsystem. Like two team members, they are working on the sapling tray, two or three are working on the pickup mechanism, two or three are working on the conveying mechanism, few of them are working on the digging mechanism. So you can provide them the area, like this is the constraint, and this constraint only you have to design, sketch, or draw anything. And later on, you can pick those subsystem from every team member and try to accommodate into a box. So it's completely on you how you want to proceed. Then once you placed all those subsystem, then definitely you should have one strong frame or chassis or the base design on which you will be mounting everything, like the subsystem or the secondary member. Make sure that main frame it is having a good mounts, that three hitch point which we have given in the rule book, placed very well so that every primary member over here is strongly connected to this three hitch points so that you won't see any damage while working or while performing the task. Then you can decide like whether you want the ground wheel on the side or one in the center. Like there are always an opportunity. You can completely hang your implement on the three hitch point of the tractor, and the tractor has the capacity to move it up and down. So it can be a cantilever, or if you want to roll it on, or you have to make sure that our implement should always be placed on this base wheel, then you can do that also and take the drive from there. Or you can have a center ground wheel and you can simply take the drive. Other thing is once you decided all the things, then it will be very easy for you to draw the secondary members. Those secondary members will be responsible to connect the subsystem and the mainframe. So secondary supports will play a role of bridging the gap between the subsystem and the mainframe. So yeah, that's it from my side. If you have any question related to this architect, you can simply reach out to your mentors, or there are many open forums which we have provided. Every Friday also you can come up with your question and ask. So over to you, Sachin, if you're here.
I think let me make Aisha, if you're there, Sachin Jangam, can you make him the presenter?
Hello, sir.
Can you make Sachin? I got him.
Sachin.
Yes.
I got it. Go ahead, Sachin.
All right. Go to the next slide. Okay. So basically what we are trying to do here is trying to give some overview about how we select the material. So for the non-structural members like shields, like packaging things. Okay. So with that, it is mostly lighter steel version can be used, and mostly like it is in the range of 0.8 millimeter thickness or 1.6 millimeter thickness, or in the commercial language, gauge 16 or gauge 18 material can be the appropriate one. Okay, 304 steel. Is being used extensively, and it has a wide range of thickness as well. So basically what we are looking for is to find out a material which will be corrosion resistance, high temperature sustainability, and it should be having a very good welding ability, and bending of those parts should be simple, and heat treatment can be provided in case if we are having that requirement, and it should be a good machinability as well. And these are like structure non-structural steels. These are like easily available in the forms of sheets, tubes, strips, bar plates, and so on. Okay. So for the structural members, S355 is extensively used as a structural member, which is easily available at the rate 80 rupees per kg, and it can be available at a wide range of thickness as well. But definitely we have to use it for a structural purpose, like vertical supports, beams, and for that particular area. For the then for the these are like, structural steels are mostly being used for the transfer the loads. So whatever the load carrying path is, load carrying path is there, we have to place these parts or beams in such a way that they will be able to carry the loads as well. So these are nothing but structural steels. Okay. So 304, 302, S355U, these are like easily available in the market, which is for the structural and the non-structural applications also. Any questions so far?
Normally what they will do, they'll put in the chat. I think you can continue.
Okay, all right. All right. Do we have the next slide? Divya, are you available? Sarfraz, we would like to cover this slide since Divya is there. Sarfraz?
And Sarfraz will be covering the bearing part.
You can continue. I think
Yeah.
you don't have
Thank
much
you.
time. That's fine. Sachin, Sarfraz.
It's
Okay.
Sachin goes on mute. No.
Yeah.
So-
Hello, good afternoon.
Go ahead, Sarfraz.
Okay, so generally this slide targets about how we can use which parts like steel parts, the plastic parts or fiber parts where we can use. Mostly for the load carrying members we use the steel parts, right? And basic requirement is we need all these stresses loads are carried before you use those. And then once you have that primary part or the mainframe supports or everything, and we use plastic or fiber parts as a coverings, right? So mostly they are purchase part, no need to go into deep like what they are, how to select them, how to design them, all those things, right? You can easily purchase them in the commercial. Okay, I think that's all. Dharmendra, you can go ahead to the next slide.
The bearing Sarfraz, you
Yeah,
let continue. Okay.
yeah, the most important part where some of the machine elements are rotating, the bearing selection is very important, kind of bearing design, right? So this, whenever you have some a project with rotating parts as a members, right, then we need to support them, we need to guide them, and also restrain them, right? So at that time we use bearings. So they also carry loads. So generally I will cover here how to select the bearings, what are the criteria you need to see. And when you are presenting your project at the end of seminar or end of the where you want to present your project, so it is important, everybody will ask questions, how you are able to come with the conclusion that this is the bearing I'm going to use, this is the good bearing for my um, project. So that kind of questions you need to check, and I will try to help here in some of these slides. So kind of a bearing design. Yeah, Dharmendra, go ahead next. So there are a lot of bearing types. So I have captured here 15 of them. I will not go detail so most important bearings are ball bearing, roller bearing, taper roller bearing, needle bearings, right? Needle roller bearings. So some of the most widely used bearings, right? Unless if you have some specific usage, then you can go for other bearings that are mentioned here. Otherwise, if it is general use, right, mostly the load they carry, the environment in which we are going to use them, right, those of the factors and also the loads will determine which bearing we are going to use at a particular case. So with that in mind, like ball bearing, roller bearing, taper roller, needle roll bearing, so we will go more into details of these into the next slides. Yeah, the one aspect, the first aspect, while considering the bearing, which kind of a bearing I need to use. So we all know that there are two kind of load acts on this system. One is the axial load, that is parallel to the shaft, and one is the radial circumference on the diameter of the shaft or the bearing. So there are cases where you will see both the loads are acting uh, like combined loads. So you need to consider at that time both the loads. An important thing you need to take care here is the axial load or the thrust load, direction of that axial load, in which direction it is acting. That is also determines how you place your bearings into the system. Okay, yeah, Dharmendra, go to the next slide. And in detail, I will just like to cover, if you see, if I just consider just a radial load acting on a bearing, and if I go to the commercial and select which one I want to use, you will see I have mentioned as a symbols here, the field round is good, square is excellent, and triangular is the fair. Okay, and the others are like unacceptable, direction, both direction and only one direction. If I just try to explain one of them, say if there is a radial load acting, you can use all of these bearings: deep groove ball bearing, angular contact ball bearings, or taper roller bearings. They all work, right? Is that the only one aspect I need to see? No, there are other aspects also I need to see, like vibration or impact load, whether it will take a vibration or not. Is it okay for the high speed? Is there misalignment allowed? What is the cost? I have not covered here, but you can check what is the cost aspect of it. And is there any uh, uh, noise or torque requirement is needed? Whether the system is rigid enough, right? Those are the things you need to consider, before you go for one particular bearing type. Okay, next slide. Okay, so let's say like you have two bearings are selected. One is the taper roller bearing and another one is the ball bearing. So now you want to make sure that which one I need to go ahead, which bearing I need to take. So as I said, other parameters in the earlier slide, here also some of the important aspect of these rollers, like if you say just for taper roller bearings, these are excellent for radial or combined loads. Excellent shock and vibration resistance, good debris tolerance, right? Because they are all covered, and then cost effective, driven by industry volume. Most likely you will get all these with high cost if you compare with the same kind of a bearing with the ball bearing with the same application. You see the cost is very high for the taper roller bearing, right? The other thing you need to consider is the complexity to achieve the setting. So whenever you use the taper roller bearings, there is a torque requirement comes, and the torque requirement, the complexity or the tolerance is very tight. If you lose, then all your system will break in few hours itself. So what we need to do is, like for the simple systems, is generally a lot of people go with the ball bearings, right? Excellent in high speed ability, ideal for low noise, low torque. Generally we don't do any torque in the systems unless there are some other requirements. Can handle axial and both directions, right? More tolerant if you have enough misalignment, like, then also you can go for ball bearings. No settings are required, as I said, no torque is required here, so then no setting. Very intolerant to shock impact loads. You can use for some simple applications, not for high load or high stresses applications. So the first thing you need to consider the load, and then second thing is other parameters, like what is your cost aspect, what is your system doing, right? Whether you need constant system or open system, how you are going to use the bearing, whether it is on the shaft which has more tolerance, tight tolerance, or loose tolerance, right? So you check all those things, but most likely we would like to go for ball bearings. It is up to your design, what is your design telling you to go ahead, right? Okay, and then Dharmendra, go to the next slide. Okay, so you have determined the loads, your application, right? What is your machining tolerances and all that, and then you need to go for some other things like what is the life we are expecting, what is the shaft diameter I have, what is the diameter, outer diameter I have, wheel diameter I have to put this bearing into it, sleeve diameter, right? What is my average speed that I'm going to use it, uh, and ambient temperature. Most likely we'll take ambient temperature as 20 degree for the calculations, right? And then rating, how much you are going to use your system. Say if I'm using this bearing in one of the shafts, which is I'm taking as a life of like 600 hours in an entire year, or I just need this to be survive for 100 hours, right? So that I can use it for just 1 month in 1 year, like that. So you determine all those things, and then try to understand what is your interface. Do you have your outer uh, rotating diameter or the inner one? So which one you want to use it, where you want to use it, right? Which is that, is it shaft rotating, or is the outer diameter, or the tube is rotating, right? And then based on that, there are certain aspects you need to keep in mind, right? If the inner diameter is rotating, then you can go for the loose fit possible, right? Otherwise you can go for interference fit. Mostly interference fits are for taper roller bearings. Otherwise for the ball bearings we generally go for loose fit. That is what we have seen in the earlier slide, where it shows like misalignment is acceptable, right? So once you come here, so gather all these details because these are important. So once you gather all these details, then you need to calculate the life, right? What is the life um, that I need, right? We need some of the life hours like 100 hours, 600 hours, but we need to convert that into the bearing parameters. That means if you go to the next slide, am I audible? Okay, sorry, it's already updated. The next thing you need to do is the bearing calculations, right? So bearing calculation is very important while you design your system. So basically you want to convert all your life into hours, right? How many hours of life you're trying to get for the calculation. Generally it comes in millions, right? And then I will not go into detail like what are the things you need to check for that, right? So basically you need the basic dynamic load rating and the dynamic equivalent load rating. So why you need, because once you have this load data, you can directly go into the supplier's website, put these values, and then there may be a recommended bearing type will be appear, and then you can go and buy that uh, bearing, or even you can just give these dimensions um, in the market, and you will be given with some suggestions which kind of bearing you can use. So that is basically we will come into, right? uh, Once you have all this data, you can just put some of these basic dynamic load rating, dynamic equivalent load rating into the formulas like I've given here for C by P, cube root of C by P, right? So you can calculate the life in millions, and then you can convert it into hours. Uh, that means you can go to the next slide. Okay, can you click into that link? So it will take you to the supplier website. So this is just for example, right? You can go, you can check your own. There are different suppliers, right? Apart from SKF. So you can just go there and put these values. Mostly it will ask you the inner diameter, outer diameter, width, and then load ratings. If you provide all these four data, then they will recommend the bearings which you can use in your systems. Then you can use directly that one. May not, I don't think so it's working, right? Maybe you guys can check it later.
So, well, I have shared only one screen, so it is
Okay, no
Clear
issue.
on this, and they won't be able to see. I have to reshare it. Even you'll be sharing this to the student, so they'll be able to open the link.
Okay.
Yeah, separately they can open the link.
Yeah, basically, like I said, you need to enter the diameters, inner diameter, outer diameter, width, and then the load ratings, both the load ratings. If you enter, then automatically some of the bearings will appear, the recommended bearings, and then you can select it and then go into the market and purchase it easily. Okay, so once you have this bearings ready, right? Bearing is designed. Now the thing is you want to take care of that bearing for the intended life, right? You calculated some life, you expected some life, but we want to continue this bearing for that life. So what we can do? So the main thing you need to do is greasing or sealing, the lubrication we call, right? So there are some bearings we just grease them. They are like contact type, right? Um, contact type, non-contact type, or labyrinth seals. Different types of seals are come. Whether you can use to seal them, not to seal them, it's depend on the application again. Mostly the ball bearings, you don't need to seal them, you just grease. That is sufficient. If it is taper roller bearing, then you have to seal it so that the lubrication should stay there for intended life. And then if I go about type of sealings, right, the bearing for bearings, the contact type is going to apply constant pressure mostly on the inner ring, the inner diameter, right? If you want to use that, then you can use as a contact type. When I say non-contact type, it is only for the outer side, outer ring, right? So both of these will not retain this lubrication. So if you want to retain the lubrication, you have to use labyrinth seal. Labyrinth seal is combination of both contact and non-contact. It seals both the inner and outer rings completely, so that your lubrication it will not be lost. It will stay there for intended life. Why we need lubrication? Because we do not want any temperature rise in your system when it is going at a high speed, right? And it will go for longer life. It can take load ranges, right? For all those purposes. If there is a no lubrication, you will end up your bearing um, fracturing or cracking much earlier than the intended life. So is there any questions we can take, or maybe we can take it later? So
At the end, we are planning at the end.
okay, sure. Yeah, thank you.
Who is taking this session?
I think Akshay will be taking the hardware selection. Akshay online.
Yeah. So you can speak now. I think you are unmuted.
Hello,
Mm.
you can hear me
Go
well,
ahead.
right?
Yeah.
Yes, Akshay.
Okay. So we'll talk about this hardware selection part in this session. And whenever you want to select the hardware for any application, you need to follow um, certain steps. You need to ask certain questions to yourself, like what type of application you are working on, where you want to use um, the hardwares, whether you want to join the two parts or you want to use the hardwares for any structural uh, support purpose. So I have listed few of the questions which you need to ask. You can start, you can go through these questions and examine yourself, like what you wanted to achieve with that. So first is like identify the application, which I just mentioned. Then you need to also consider the load requirement, what type of maximum load is going through that joint, whether it will be a static load or dynamic load. Then you need to understand what type of material you are dealing with, whether you wanted to uh, join the material steel or the plastic or the rubber, like that. Then you need to also determine the type of joint you want, so that will be dependent on the application. So we'll see the type of joint in the consecutive slides. Then you need to also consider the environmental factors where you will be using that joint, whether it will be susceptible to high temperature or moisture or certain chemicals, or it will be open to like vibrations like that. And you can refer some standards like ASTM standard or ISO standards for um, selecting the type of hardware. And you can also seek the some expert advice for selecting the hardware if you are struggling with some specific problem and things like that. So this is about the certain questions you need to ask to yourself while selecting the type of joint. And in the next slide, we'll see type of the joint we have. So Dharmendra, if you can move to the next slide. Yeah,
Next slide is type of fastener.
yeah. So so these fasteners will come into different types like bolts, screws, nuts, washers, rivets, nails. Every type of fastener or hardware will have its specific purpose. Sometimes you can use just the bolts with the threaded opposite part, and you can fasten the two parts. If you want to use uh, the the wood or plastic, you wanted to have a self tapping feature in that, so you can use the screws. Nuts can be used in combination with the bolts. Washer can be used to kind of secure the joint well, have the better stability in the connection. You can use rivets when you do not want to service the part. It will be a kind of a permanent joint. So in that case, you can use the rivets. You can also use the nails in the specific application, um, maybe in the woodworking or some construction applications. And then you can also use some kind of clamps if you want to join two maybe hoses or springs together, so you can use clips or clamps. And if you want to lock some kind of a joint, you can also use the uh, dowel pins or the normal pin with the cross bolt like that. So these are types of fasteners or um, the type of joint you want. Based on that, you can select out of these. And then maybe we'll dive more into the threaded fasteners, when to use the threaded fasteners. So out of the previous fasteners, specifically if we talk about the bolt and the nut, that is most commonly used type of fastener. So when you want to service the part, or when you want to assemble and disassemble the parts, that time you want a joint which is easy to assemble and disassemble. So threaded fasteners or the bolt and nut type of the fastener is something which you can um, uh, remove and assemble frequently. But if you want to use the joint as a permanent joint, then you can use as a uh, welding as a one of the method, or the rivets or some kind of adhesives. So that uh, like these are the two types which mainly dictate what type of fastener you will be using. So threaded fasteners are for the service purpose, and there are some other parameters which are dependent, which depends like uh, based on that you need to select the type. Like sometimes the cost is the factor. So if you are using the threaded fasteners, then the cost sometimes increases because of the mass increase. If you want to reduce the cost, then sometimes you would select uh, the welding over the bolt-on connection. Sometimes you will be having some kind of assembly constraints or the space constraint. That time you might need to select the bolt-on joint. So yeah, these are kind of some criteria which you need to keep in mind while selecting the type of fastener. Terminal, can you move to, yeah. So we'll look into the types of bolts. Um, so we know like we have hex bolt or hex flange bolt. Apart from that, we also use carriage bolt sometimes when we do not have access to the head of the bolt, or we wanted to have the smooth feature of the bolt head. That time we use carriage bolt, which has dome-like shape, and it has a neck of a square shape generally. So that bolt would not need to hold from the head side. We can just torque it from the nut side. Um, then there are some other types of bolts as well, like the lag bolt or eye bolt, U bolt, studs, J bolts, or shoulder bolts. Each has its own different application, um, and based on need, we can select them. So yeah, these are the types of bolts. Mostly we'll cover the hex bolt here for the calculation part in the next subsequent slide. In the class of the bolts, you might have seen in the hex bolt head will have notations like 10.9, 8.8, or 12.9. So what these numbers is dictate is like 10.9 means it's um, 1000 MPa tensile strength bolt, to be precise 1040 MPa, and zero point 0.9 factor is dictate the yield strength of that bolt. So if you multiply 1040 or 1000 by zero point 0.9, you will get 900 MPa value. So that uh, value is the yield strength of that specific bolt. So this is how you will understand what type of bolt it is, what grade it is. Higher the grade is, the stronger the bolt is. So that you need to select like if you want to use a bolt with a higher clamp load capacity, you will be choosing the bolt with the higher grade likewise. And you need to also select the equivalent quality of the nut for that bolt. So we'll see some calculation part in the subsequent slide. So if you want to design a bolted connection specifically for the hex bolt, which we generally use in the agricultural application, um, or into automotive, we need to follow these steps. So we need to understand first what type of external load is coming on the joint, and you need to calculate that value first before starting the design of the bolted joint. Before selecting the number of bolts and things like that. So first you need to first you need to find out this external load coming onto the each joint. Then you need to calculate the stiffness of the bolt and stiffness of the joint, and that will dictate how much part of the external load will be carried by bolt and how much part of the external load will be carried by joint. Then you need to calculate the portion of the external load taken by the bolt, and then in the fourth step you need to consider the preload which is getting generated while torquing the bolt, and you need to calculate that, and that will be used in the fifth step, like for comparing with the yield strength. So first you will be calculating using that preload, and then you will calculate the tensile stress in the bolt, um, and then you will calculate the yield factor of safety of the each bolt. So these 6 steps you need to follow. Maybe I can repeat quickly. First, you need to find out the external load. Then you need to find out the stiffness of bolt as well as the joint. Then you need to calculate the portion of the external load taken by the bolt. Then you need to calculate the total bolt load, which is like preload plus or minus external load after application of the external load. Then you need to calculate the net tensile stress in the bolt, and then you need to calculate the yield factor of safety of the bolt. So yeah, these are the steps you need to follow. Dharmendra, maybe you can move to the next.
Yes, actually, Akshay, just one request if you can be quick,
Yep, yep,
because we have other slides also.
sure. So this is the last slide on the calculation part, and then I'll share some tips. So those steps which I mentioned, you can follow based on using this calculation for the bolt stiffness, and find out how much actual preload is present in the bolt after application of the external load. And based on that, you need to find out the factor of safety of the bolt in yield, and you need to also find the factor of safety in shear, so that the slippage will not occur in the bolt. And based on that, you need to adjust whether the size you need to change, or you need to change the grade of the bolt, or you need to apply more clamp load on the bolt by increasing the torque likewise. So Dharmendra, maybe you can move to the next slide. So we have some design tips here. If you want to have your bolted joint strong enough to survive for um, almost most of the applications, then you need to have the factor of safety in the bolt yield or in the tension and shear more than 2 whenever possible. So that will ensure that it will not lose in like a worst case scenario. Then you need to keep the bolts in tension most of the time. Avoid using the bolts in shear. That will keep your joint strong, and less chances of slippage. And if you're struggling with the joint, like if you are not meeting the yield criteria in both either uh, tension or in shear, what you need to do, you can follow these suggestions, like either you can increase the bolt size, or you can increase the number of bolts, or maybe you can increase the spacing between the bolts, or you can think of increasing the grade of the bolt, like from 8.8 to you can increase it to 10.9 or 12.9 likewise. Or you can increase the joint stiffness. Increasing the joint stiffness, let's say if you're joining the two sheets together, um, and the joint stiffness is less, then you can add extra washer or bush on top of the two sheets which you are joining, which will increase the joint stiffness, and it will improve your factor of safety in tension as well as in shear. So these are some of the design tips for better bolted joint design, and some general tips I have included here. So calculation part is fine, but whenever you are kind of using uh, your design in reality, you need to make sure you have proper torque applied to each and every joint while assembling the parts, to avoid the joint failure during the competition of TIFAN and so on. You can also think of using the Loctite or lock nut for critical joints where you see the possibility of increased vibration, or you have a critical joint. You can also use some kind of positive locking kind of quarter pin or cross bolt for like high risk joint like spindles, hubs, like that. and you can maybe this one is the best tip I would say, like try to use standard joints from similar applications in automotive or agriculture applications. You can easily get those standard joint if you want to use in your application, like in your machine. Then you can uh, kind of select that, and you'll easily get that from any of the service dealer of that product. So yeah, that's it from my side.
Who's taking this section?
Uh, yes, Abhishek, you can speak now.
Yeah, so good afternoon to all. So this is about the welding part of the structural design. So as Akshay already explained, that when we are designing the components and when we are designing the connections, there are chances that we have to make the designs as serviceable and as non-serviceable. So in the case of serviceable joints, when we want to change the components and when the parts need to be removed a couple of times, so you have to choose the bolted design because that is easy to unclamp and clamp it again. But when we talk about the permanent connections, the welding is the process that is the most economical one, and it creates permanent connections which are having a good strength, and the strength of it is as good as the strength of the base material. So I guess for the welding, we are all aware that the basic process is that we are connecting two materials by fusion with the use of heat or pressure. And as I said, that it creates a permanent joint, and it is also a preferable method of joining where your space or access is limited for mechanical joining like a bolting or a riveting. So in that case, the welding does help to put us connection and to secure the parts together. So there are many types of welding that we are using in the industry, as well as thing we have gone through all that literature. So for the stick welding, like I think the most common part of the welding that we use is the arc welding that we do. And then from the industry point of view, there are other welding practices as well based on the materials that we want to connect and based on the strength of those materials and the amount of weld time that we have to complete each of the connections and how much the welds are automated or welds are manual. So based on that, there are various techniques like MIG welding or TIG welding or laser welding. In specific, like laser welding is used when we are going to connect very thin material to each other. And we have good strength for each of those laser weldings, but the only thing is that that is a very skilled operation. So that is usually seen in the automotive application and in the heavy equipment application. For the I think designs that we are going to work on, the stick welding is going to be the easiest one and the most common one. So I think we can move to the next one. Reminder, can we switch to the next slide, please? Yeah, thank you. So these are the common types of our welding joints and the type of welds. So depending on the connection between the two parts at what junction you are trying to connect those, the type of weld joints can be there, like a butt weld, kind of a T joint is also possible. Lap joints are also possible when you place one part of the metal on the other. Then also a corner joint is possible where you're connecting some kind of tube to each other at at a junction where two perpendicular or let's say at a different angle the tubes are connected. So those are the kind of different joints that you will be going through while you're designing your parts and design or making those connections in your structure. And then majorly there are two types of weld. One is the filler weld where we are having penetration in case of the T joints. Yeah, you can say there is less amount of edge preparation needed in those cases. So we are just connecting the two parts maybe in a lap or a T kind of a position. And then the groove welds are mostly in case of, let's say, the butt welding, or where we are looking for a higher strength. So those kind of applications are there. I think we can move to the next slide here. Yeah. So while you're designing for your structure, there are a couple of things that you can consider while you are doing the calculations and when you're choosing where to put the weld actually. So while you're designing your connections, be very sure about what type of loading you're going to get on the part, and where the loads are going through. So in order to make sure that you're putting as less amount of stresses into the weld as possible. So what you want to make sure is that your material is kind of taking the load from one member to the other and not the weld. So the weld is just to keep the components together, but it is always preferable that you are keeping your weld connections in tension or compression. So the basic design criteria is that you try to use the design strength of your parent material as a parameter to define how much stresses you want to limit on the weld connection while you're doing all those calculations in a bending scenario, or in a tensile loading, or in a torsional scenario. So that you will have to keep in mind while you're doing that. And then try to keep as few weld joints as possible, so that you're able to minimize the chances of the number of defects that you're going to see in the connections or in the overall structure. So that is just a quick thumb rule there. And then keep continuous weld in the connections area where you are not able to actually transfer the load through your members, and you have to be more dependent on the weld. So try to use continuous weld there. Don't go for a skip weld, because the start and stop point of the weld are the points where there are maximum chances that the cracks will initiate, or the welds will try to set apart from each other, or the parts will try to pull apart from each other. So that's the one of the good rule that you can follow. And then as you can see in the last image that I have put up here, so try to see that whenever you are designing a weld connection, wherever your load is going to come, try to keep the route away from getting the load directly. So in this case, like you see, there is a load coming from the top. So there is kind of a offset loading to this connection where we have put that fillet. So try to back it up with another, let's say, butt weld on the other side, or maybe you can use some extension on that bottom plate to add another fillet on that other side, so that your root is not directly loaded, because root is also one of the critical points where your weld will start to pull apart, so that you can follow. I think we can go to the next one. Yeah, thank you. So some of the factors which are affecting your quality of weld after the design, like while you are actually manufacturing the things. Some of the factors are like the travel speed. So go at an optimum speed. Don't go too fast, because that would reduce the size of your weld bead. And don't go too slow, so that because it would add too much heat into the joint, and it would also reduce the chances of penetration, because the molten metal is kind of forming a bead on top of each other. So there is kind of huge deposition, but you may not see a good penetration into the connection at the bottom. Then there is a very good technique that we use in the industry as well, that the two images that you can see on the right side, on the direction of travel when you're adding that weld, try to keep your electrode at an acute angle with respect to the weld bead that you have already generated. So that kinds of pushes that weld, and that gives you a good weld connection for all the locations. Generally, we do see that even a pull technique is also used in some cases, but the quality of weld is better in case of push if you use that. Then quick tips like slow cooling is required. So whenever you weld some of the parts together, try to spare some time so that the cooling is happening slowly, so that all the heat dissipation is happening through your heat affected zones, so that your strength is not compromised and there is additional brittleness added to the connection. Then position of the weld, try to keep it in flat position. Then be very thorough in choosing the filler metal. The strength of that filler metal need to be very close to the strength of your base metal, so that will give you a good connection when you are doing the weld. So can we go to the next slide, please? Yeah. So I think that's the last one that I have for today. While you're actually making the structure, usually what happens is like we do design the structure to have the connections wherever needed, and as I explained earlier, that you are going to keep the connections at a place where your load is going through the members and not through the weld. So even though we are designing all those things very judiciously, and we are keeping all these things in mind, but in actual operation, when you are putting all that heat into the metal, what will happen is like in the microstructure of that metal, there will be a shrinkage which will happen. So that would actually distort the assembly. So you can actually do this quick, you can say trial in your lab. You can connect just four, square tubes to each other, or connect four members to each other, and you will see that after all that weld has cooled down, your square will not be able to meet all the dimensions. You will see some distortion happening somewhere or the other. So that is kind of a shrinkage which happens when you're putting all that heat. So the basic things that you can keep in mind if you're wanting to keep also the dimensions in place, because that is also important for the function to happen for the machine. So do not overweld. Try to keep as limited weld as possible. And do not weld over the weld. So that is kind of adding another, I would say, one more bead of weld on each other if you see like some gaps in some cases. So what that does is that adds more heat into the connection, and that adds to the shrinkage, as I mentioned earlier. Another thing is, like I said, wherever you are passing the load directly through the weld, try to keep it continuous. But wherever the connection is in a flat condition and there is no direct loading going through there, try to use intermediate welds, and try to space them out in such a way that they're around the neutral axis of the tube, so that the shrinkage is kind of balanced on either side. So that way you can make sure that the dimensions are not distorted a lot. And then there will be a couple more slides coming through in the jigs and fixtures. But the one thing that you can make sure is that while you are connecting all the parts together, the clamps and fixtures can help you a lot if you're positioning them well to keep the distortion in control, and you can decide the welding sequence as per that. So I think those were the quick tips. That's it from my side. Thank you.
Thank you, Chair. Yes, Sunil, you can go ahead.
Yeah, am I audible?
Yes.
Yep. As my colleague Abhishek mentioned, jigs and fixtures plays a very important role in manufacturing, but generally we have seen jigs and fixtures being used in industry basically for facilitating mass production with a very high efficiency and precision. But with the work or project or machine that we'll be working on as a design engineer here, we would have very limited resources with us to manufacture that particular machine, and that is where having a proper fixture and jig design for our application in order to facilitate the manufacturing of design that we have worked on is very important. So jig basically is defined. It's a device which holds and locates the workpiece tools. It guides the tools and makes sure that we have a very precise manufacturing carried out. And fixture is nothing but a device that is used to hold the workpiece, used to hold the, let's say, parts, sub-assemblies for inspection and as well as for manufacturing. So there, as we speak about jigs and fixtures, there are a few of the major principles that we need to consider when we try to design jigs and fixture for our application. First, we need to understand what component we are manufacturing. We need to study a component and workpiece and see what are degrees of freedom we need to constrain. If we need to constrain all of them, how are we going to do it? So study of component is very important because that would define how the fixture and clamping would look like. Then need to understand if we are, let's say, manufacturing a component with the help of welding, we are creating a joint with the help of welding. We need to understand what is the capacity of that particular welding machine, and by considering that, we need to have a fixture design. We need to have the locating elements, clamping arrangements, and indexing devices properly identified, defined in order to make sure that we have a very precise manufactured part. Then there are some of the minor principles I have mentioned at the bottom about tool guiding and cutter setting elements, which we might need to use if we have any machining components involved in our project. Then we also need to have some full proofing arrangements. This generally is required when we are manufacturing a lot of parts, but if let's say in our machine we have some of the parts which are repetitive, we would need this particular arrangement. And yeah, then we obviously would require to put some safety devices in case we are dealing with let's say welding or high heat zones. Dharmendra, if you could go to the next slide. Yeah, I'll focus on the basic fixturing or clamping principle that generally we use in our manufacturing process. That is 3-to-1 principle. We all know any object for that matter in a space has a 12 degrees of freedom, that is three rectangular displacements along the mutually orthogonal coordinate axis in xyz direction. So positive and negative, that makes it 6. And then we have three angular displacements with respect to the same axis. So that xyz, so make that 6. So there are 12 degrees of freedom, and in order to manufacture any part, what is important is to make sure we are constraining all those degrees of freedom, so that whatever manufacturing operation, be it machining, welding, or for that matter, assembling that part into a bigger assembly, we need to hold them together, and for that we need to constrain all the 12 degrees of freedom. So generally in 3-to-1 principle, what we do is we define three datums and we support those three datums with the respect of 3-to-1 supports or pins respectively. So generally for primary datum, what we need to do is whatever part we are manufacturing or subassembly we are manufacturing, we need to consider a larger surface area as their primary datum, and we need to put in three support pins, and that will ensure that we are considering 5 degrees of freedom. How, I'll be explaining in the subsequent slide. Same way, we have to consider the secondary datum, which is a next largest surface area, and tertiary datum, which would be the next largest surface area. Generally, with this 3-to-1 principle having support on three datums, it constrains 9 degrees of freedom. We will obviously have a 3 degrees of freedom, which we need to constrain by appropriate usage of, let's say, locators or clamps. So I'll probably go ahead to the next slide, where I'll try to explain about these three datums and how they're constraining the respective degrees of freedom. So the left side, you see we have a workpiece, a rectangular workpiece supported by three support pins or supports at three locations. And what it is doing is it is basically constraining the axial movement in a downward direction. Let's assume plus z, and then it is constraining two radial movements in x and y axis. So that way it is constraining 5 degrees of freedom. The same workpiece on the right side is being supported by two pins on the next largest surface area. You can see in the top or plan view, and then on the side view. So these two next locators generally are normally placed in 9 degree to the first one, and they actually restrict the movement along y-axis here, if you can see in plus y direction, and also radial movement around z-axis. So they constrain another 3 degrees of freedom. So there are total 8 degrees of freedom you can constrain with these two arrangements. And we can move to the next one, where I'll show you the last support pin. Ye- Yeah, so here in this one, what it does is we have a pin supported on the left side of the workpiece, where it is restricting the direction in the uh, plus x direction. So till now we have kind of constrained 9 degrees of freedom, and remaining 3 degrees of freedom we more probably need to have a proper clamping used for that. And in industry we have a variety of clampings available, but there are few of the general purpose or widely used clampings are mechanical actuation clampings. We have some pneumatic and hydraulic clampings. We have vacuum clampings. We have magnetic clampings. We have some of the electrostatic non-mechanical, and few of the special clamping that we might need to design for our product. As I mentioned earlier, jigs and fixtures. First, we need to understand our component and see if there is any readily available market fixtures or clamping that we can use, or if not, we might need to go ahead and design it ourselves for our parts. Next slide, please, Dharmendra. Yeah, so that was more about the theoretical part. Now I would try to run you through the basic components that we might need to focus on when we work on our machines here. So as Dharmendra was showing in the architecture slide, how the machine would be, and when he was explaining, he mentioned that we need to have a proper, strong chassis which would be supporting all the functional parts. So let's assume a vehicle or a frame of the vehicle. First, what we need to do is when we start designing or I would say deriving the fixture requirement for our manufacturing, the first part that will come in our mind is the body. That is basically it can be a plate, it can be a box, or it can be a frame in which you hold the part. So basically, it should be very sturdy and rigid because we consider this as a fixed base plate or a primary datum. So what will happen is when we have a primary datum which is very fixed, so we make sure that whatever operations we are doing, we will have multiple rounds of weld, multiple cycles of weld, and then we also might have a few of the machining operations and also the assembly operations. So having this primary datum which is very sturdy and rigid, it would help us in retaining the axis of each parts with respect to its interacting parts, and make sure that we don't have any misalignments. So that way we can have a primary datum, and then as I mentioned, it can be plate or a frame. So I have just tried to show you in the second picture on the right side, in place of uh, base plate, we can have a frame, a angle frame, which is holding it from two sides, or we can also have uh, uh, a box that can hold the part. So along with the rigid primary base datum, we can also use the locating elements like Akshay was mentioning earlier in this hardware selection part. We can use few of the dowel pins in the fixture in order to locate our workpieces, because you might be doing a lot of welding and different kind of welding, so you might not be doing that at one place. So you'll carry a part from one location to other location. So while doing so, when we do these multiple operations and bring it to the final assembly, we have to ensure that the position at which it was welded earlier is retained when they are completed with the manufacturing, and when we have started with assembling them. So dowel pins would help in relocating when we move that part from one location to another location and bring back again to the assembly bed or at the final assembly location. So we can use those as a locating elements. We can use additional clamping elements as and when required in order to ensure that our workpieces or the parts are firmly secure in our located positions. Then we can have some positioning devices where I have mentioned that we need to have a very good fixture, but at somewhere apart from the locating elements, we need to hold that fixture against the workpiece. So we can use the positioning elements. And in case we have some indexing operations like certain machining operations being done at certain angular position, we might need indexing elements. So these are the major jigs and fixture elements that we need to focus on while working on our machine here, to ensure that whatever design we have made, we are just translating same into manufacturing. So this probably would be last slide from me for the day, where these are general industry standard material that we use for different jigs and fixtures. Probably for our usage, we would use mild steel or high tensile steel and high speed steel, because the generally mild steel is very economical and it is most widely used in most of the jigs and fixtures. So whatever jigs and fixtures we might need to design for application here, we might be end up using mild steel. But if we have, let's say, uh, a fixture requirement for machining, or I would say heavy drillings, wherein we have a lot of stress being generated, we might need to use some of the high-speed steels or tensile steel. And others are for your reference. Maybe you can refer to that. Yeah. So that's it from my end. I'll hand it over to Yogesh for analysis part of it. Thank you.
Thank you, Sunil. Yogesh. Yes.
Okay.
Thank you, Sunil. Thank you, Dharmendra. Good afternoon, all. I hope you all are awake. Detailed discussion, lot of learnings. So we are gonna talk about the basics only, which you have learned in your normal subjects. So we will just brush up those concepts, which will help you to do analysis of your parts or whatever you design. So basically, we get uh, types of loading, we can say. So first type is tensile loading, wherein we pull the object. Then another type is compression, so wherein we push the object. Next is shear. So here the cross section goes, in these two cross section remains same, but here cross section, I mean, uh, we can call this as a distortion. The shape will not be same. And then bending because of moments and all. So in case of beam, we see this. So these are all the loads that we see in our uh, normal operations on our machines and parts. Shall we go to next slide, Dharmendra? Yep. So because of all those loadings, what is generated inside the material? So first thing that comes to mind is stress. Stress is resisting force upon area. So this is the area which is resisting, and this is the force. So I called resisting force because this is reaction of material to this external force. So that's why resisting force upon area. Unit is Newton meter square or Pascal or megapascal also. And then next is strain. Yeah. Strain. So strain is change in length upon original length or change in dimension upon original dimension. It is unitless and pretty straightforward. Yep. The next thing is stress strain curve. So for ductile materials, especially for steel, we have seen this stress strain curve. Till this point, it is elastic region. In elastic region, our stress is directly proportional to strain. Hooke's law is obeyed. What is Hooke's law? We're gonna see, but that is obeyed. Then this is very small portion. Uh, this portion is plastic zone and this portion is yielding zone. But practical point of view, we just neglect this portion in industry. So we are more interested in this and in this. So this is strain hardening zone. So in strain hardening zone, strain increases more rapidly compared to stress. So the force which we apply results into more deformation compared to resistance or stress. So this is nonlinear zone. And then beyond UTS, we have necking and rupture. Uh, so this is all about for ductile material. For brittle material, the curve looks like this. Oh, Dharmendra, you are moving. I cannot move it. All right, thank you. So uh, for brittle material, basically we just have two zones, and strain hardening zone or plastic zone is very small. Mostly it is elastic zone. For brittle material, we usually use offset method to decide on the acceptance criteria for it. Like to decide the yield strength of the brittle material, we use 0.2% strain, and corresponding to that, whatever stress comes, that we assume as a yield stress or proof stress, we call it, for brittle material. We will more see about it in acceptance criteria. Yeah. Uh, some of the governing equations within proportionality limit, our stress is directly proportional to strain, a constant known as Young's modulus. So this is applicable within proportionality limit only. Then Poisson's ratio. So ratio of lateral strain to longitudinal strain. So let's say on any material, if you apply tensile load, you will be pulling it. So because of that tensile load, the cross section decreases along the length. So that is longitudinal strain. So ratio of those two strains is your Poisson's ratio. For most of the metals, Poisson's ratio is in between 0.25 to 0.35. Uh, that is for most of our metals, and for plastics and for other materials like genetic materials, there is, I mean, it could be negative also. To define material for any analysis software in static analysis, we just need these three things: Young's modulus, Poisson's ratio, and density of material. So we can go to next slide. Yep. Then one more thing, like degrees of freedom. There are 6 degrees of freedom: translational, 3 translational, and 3 rotational. So these are some of the classic examples, like fixed beam. For 2D case, we have Fx, Fy, and moment. For pin or hinge support, we have Fx and Fy, and for roller support, only Fy. So all others are released for these things. Similarly, for ball joint, we have all 3 rotations released, whereas translation is fixed for it. For bolted joint, all degrees of freedoms are fixed. We do not see rotation, we do not see translation about it. We can go to next slide, Dharmendra. Simple example we just tried to take to show you hand calculation and how FEA shows the results. So this is a cantilever beam. There is a point load acting on it. This is square beam. Input for this is cross section, then load, length, and then material properties. So we are assuming steel, so 200 GPa, Poisson's ratio of 0.3, and 7850 density. Boundary conditions are shown. It is fixed at one end. So we can go to next slide, Dharmendra. Yeah. So uh, if you wish, you can draw shear force diagram and bending moment diagram for it. For drawing shear force diagram, what we can do, we can just draw FPD of this. It will be a straight line, one side P, and the reaction force from bottom, it will be P. To calculate shear force diagram, uh, take any cross section and algebraic sum of forces either to the right or to the left of the section should be uh, equal to your shear force at that point. So we have, let's say P is the force, so P will be our shear force. So it will be square, rectangular shear force diagram. Sign convention, generally I take right side upward negative. So this is downward, so this is positive, and then this will come down negative. For bending moment, we can just calculate the bending moment P into L, and then that will be maximum here and straight line. So now, no, Dharmendra, that's, yeah. Now coming to calculation part of it. So stress, like maximum deflection is 2 mm for this, and stress is 600 mm for this. So deflection we can calculate from deflection formula, and stress is from bending moment equation. So sigma by m is equals to I by y. M by I is equals to sigma by y. I cannot write, but bending equation, you know. So based on that, the I for this is 1 by 12 into 8 to the power 4, and we can calculate I. Y is half of this length, that is 5. So you will get 600 MPa. And same thing if we simulate in FEA. So this is the beam that we have simulated. We have constrained here. So you will see a deformation of 2 mm, at the same time stresses of 600 MPa. So here we are getting 600, here we are getting 600, 601, or on bottom side 605. So generally 5 to 10% of variation we take it as an acceptable range, because FEA has its hidden drawbacks or lacunas. At the same time, classical formulas also have their own merits and demerits. So a good approximation is 10% here and there is accepted. We can go to next slide, Dharmendra. Yep. Type of element that we use in FEA. So 1D, when one dimension is very large, shape is line only. So this is rod, beam, bar elements. We need to define cross section for them. So they will be like this line element, beam, rod. Sorry. So we generally use them when we are not okay, we are close to finish. I will just quickly run through. For 2D, we have quad and tria element, so they look like this. And for 3D, we have tetra, penta, and hexa element. Generally, 2D we use till 10 mm thickness, and beyond 10 mm we use 3D in elements. We can go to next slide, Dharmendra. Type of contact. So let's say these two beams are there. We have applied force on top beam. So if there is no contact, the deformation will be like this. This will not move in FEA. Whereas in actual case it should move, so that's why we need to define contact here. If we define, it will move like this. There are two types of contact. So linear contact, like bonded contact or no separation, so they will assume there is perfect contact, like this will be like a welded joint. They will assume it is perfectly in contact and it will not separate. Whereas frictional contacts, they assume some relative movement between these two, uh, considering the shear coefficient of friction that we give. Generally for steel materials, we use 0.15, 0.12 to 0.15 as a standard friction uh, factor or coefficient of friction. Next slide, Dharmendra. Theories of failure. So this will help us on deciding the acceptance criteria. Maximum principal stress theory is generally used for brittle materials. So here we are using maximum principal stress less than sigma u, but we should not use UTS, we should use the proof stress. So proof stress is the value corresponding to 0.2% strain that we have seen on earlier slide in offset method. 1 we use for ductile material, and maximum shear stress also for ductile material. So mostly for principal stress for brittle and 1 for ductile. We can go to jump to next slide, Dharma. This is last slide. So factor of can based on strength, durability, we can decide the acceptance criteria. Factor of safety, like whatever factor of safety we need from yield or from endurance or from tensile strength, that we can decide based on material, based on the loading condition and how many cycles we are gonna experience. So based on that, we need to decide this stress. So yield or ultimate, what is our acceptance and what factor of safety we are considering. So dividing yield with that, we can use it as acceptance. Based on type of event means how many times that event will happen. So if it is high cycle, then we can go for endurance and life of component. So again, fatigue life will come into picture, and based on that, we can decide whether it should be endurance or yield or what. Uh, I think this was my last slide. Dharmendra, do we have anything after this? No.
No,
All right.
Yogesh, think
So
did it on time. Everything is
thank
very well covered.
you. Yep.
Thank you.
Thank
Girish.
you.
Ajay, you are not audible. I think your microphone. No. Hello.
Now, can you hear
Yes.
me?
Yes.
Yeah, as I was saying, I think we can extend for 4 more minutes. So any specific question for this team from students? As I said, this recording as well as the presentation will be available as a web page soon. But if you have any questions, the presenters are here. And can presenters switch on the camera for a minute? Damodar, YouTube, Sunil, Abhishek, Akshay, Harshaz. I'm becoming black. Yeah, Akshay. And I think Sarfraz there. Fine. If no questions, I think we can, can close the session. Thank you very
It's
much.
just a few one comment I would like to make here, Ajay. Students, so the technical team who presented the slides, they have been given a very less time to prepare the slides. Hardly 2 days, 3 days were given, and they took out the time and prepared the slide. Almost the biggest challenge in front of them was they cannot use any handy images or anything from the online sources, available sources. So you might have seen some of the handwritten words, drawings, or the images prepared in the slide deck. So they have that with their hand. So definitely you should be thankful. And from my end also, I would like to thank each and every one of them to do it in a challenging time frame. So yeah, thank you once again, everyone.
And sorry for giving a challenge that we can't use Google Images. Yeah, that's something which we have to do it.
Yeah.
You will get the recording, team, as I said. It will be in the same webpage as Aisha's recording. She will post it as soon as possible. So the link is already there. So thank you very much.
Thank you.
Yeah, thanks. Aisha, we can close the recording. We will put answer how to do a personal for 3.8 system team will put answer on captain's group.